So if we summarize our previous session, then we'll discuss about how to find out critical damping coefficient of any mechanical system. So we have taken example of two mechanical systems. One is our simple spring mass system. So for that we got this Cc is 2 square root k by m, and second we have taken this type of rotating system. So rotating disc which is connected to one torsional spring and one damper. Then for this type of system, what should be the critical damping coefficient? And what is aim of critical damping coefficient? That critical damping coefficient gives the value of external damping which is required to mix system such that it would not oscillate, right? So that is what the purpose of critical damping coefficient, right? So we have also found critical damping coefficient for simple pendulum. So if you arrange a damper, this damper with the damping constant equals to this value, damping constant is equals to this value, right? Then that pendulum will not oscillate. Means if you disturb it by angle theta and if you release it, then again that will come back to the mean position without oscillation, right? So that is what the purpose of critical damping constant. And then this problem was given as task. It's a torsion system, again rotating torsion system, but here we are having fluid surrounding to this disc, right? So this task was given. I hope you have tried to find out critical damping constant for this type of system. So if you have solved this, then you can share value or the equation of critical damping coefficient for this type of torsion system. So what you got, can you share now? Janish, Karthik, have you tried?
No, sir.
ટ્રાય
અડધું કર્યું હતું.
Okay.
પેલું થયું નથી.
Yes, Karthik.
ક્રિટિકલ ડેમ્પિંગ વાળું મળ્યું નથી હજુ તો. થોડુંક ટ્રાય કર્યું હતું.
Okay. Let me quickly show you how to find out critical damping constant for this type of system, because we have similar system in our laboratory where we'll be performing practical. So this will be helpful to you, right? So let me show you. First of all, we need to draw free body diagram. So you can consider this rotor. Now we are assuming that this rotor is rotating in clockwise direction. So in this clockwise direction, this rotor will be having inertial torque, right, which is I theta double dot. But as I told you, this wire is having stiffness kT, so that will not allow this rotor to move in this direction. So that will produce some opposite torque in this direction, which is torsional stiffness of wire into theta displacement, right? But now this time, if this liquid carrying drum is not present, then only these two torques are present. Then as per Newton's approach, we can write this as I theta double dot is equals to minus kt, which is torsional stiffness of wire into theta, right? But now this disc is kept in liquid containing drum. So suppose you know that C of this drum, let me change it, this will help you to understand. I'm using same color. So if you now consider C value of this drum, then you know we have derived it is mu A by H, right? Where mu is the viscosity of fluid which is filled in this drum. A is the area, means if you open this cylinder, then you can imagine one rectangle which is equals to length 2 pi r, means if you know about the development of surface, right? So if I open this disk, then length of disk will be 2 pi, and if the radius is r, then 2 pi r is the radius, right? And width is suppose b, then 2 pi rb, that is the area of this disk, so that you can easily find out, right? And h is nothing but this gap, means this annulus gap between outer surface of disk and inner surface of drum. So this is what called as h, right? So this is what the equation, c is equals to mu a h, right? So this much of external damping we are giving to this system, right? So now due to this, it will also experience some opposite damping. So that I am mentioning as this c, I am mentioning here c into velocity and rotating velocity of drum, sorry, of this disc within this drum, because drum is stationary, right? So this will be the equation based on Newton's second law. Now let us take this both the negative terms on left side. So equation will be I theta double dot plus c theta plus k t theta is equals to 0, right? And this c is nothing but this term, right? This c which is written here, it is nothing but mu a h. Okay. So now will you please tell me what would be our next step? Because this is what we have done in last lecture and in so many lectures as such. We got this equation, right? We got this. Now what is our next step? We imagine displacement is as a simple harmonic displacement, right? So same we'll do here. We'll assume this theta, we'll assume that theta is equals to some constant and simple harmonic motion s of t, right? So this is what theta. I want theta dot as well, means angular velocity. Then let's take theta dot. Then theta dot is differentiation of this. Then we will get x s e to the power st, right? And we also want theta double dot. So acceleration is again differentiation of this velocity theta dot. Then theta double dot is equals to constant as it is s square e to the power s of t, right? Now what is our next step? We put this all theta values in this above equation. Then from all these equations, if you look, then xst is common from all, and that is moved on right side, then that becomes 0. Then again we'll get I s square plus c s plus kt is equals to 0, right? Now will you please tell me what would be our next step then? This is what the quadratic equation of s. Then what are the roots of s? We'll get two roots, right?
Yes.
S1 to
Minus c plus or minus c square minus 4 I kt, right? And this divided by 2 times I, right? Now
S.
how to find out critical damping constant? We need to make this term which is within square root equals to 0. Then this c becomes cc, critical damping constant. So this cc is equals to, if c square minus 4I kt is equals to 0, then we can say Cc is equals to 4I kt and square root, right? Is it clear now? So this is what called as equation of critical damping constant for this. Means now if you put value of I and kt, then you will get some numeric value. Means if I give you I is what for this disk, I is 1/2 m r square for disk or for cylindrical shape, right? So if I give you mass of this disk, I give you radius of this disk, then you can find out what is I. So that I you can put here. If I give you what is the stiffness of wire, what is torsional stiffness of wire? Let me give you. It is what? C theta by L. If you remember, it is sorry, it's not C theta by L, Cj by L. Let me show you. If you consider the torsion equation, which is, let me take one new page. So I is what? 1/2 m r square. Now suppose if I tell you mass of this is 5 kg and radius of this is suppose 50 mm, right? Then you can find out what is I. Okay, similarly, what is kt? If you recall, T by J C theta by L. This is torsion equation. Then what is kt? Kt is T by theta. T by theta. So form T by theta from this equation. Then what we get? T by theta is equals to Cj by L, where C is what? C is what? Modulus of rigidity, right? Modulus of rigidity in megapascal. J is polar moment of
Polar
inertia.
moment
If
of
it's a
inertia.
circular section, then it's a pi by 32 d raised to 4. If wire is circular, then and L is length of wire. Means now if I go to this plot, then length is this, cross section area of this wire, we assume it's a circular, then you can easily find out kt if I give you all these values. What is C, what is D, what is L? Then by putting these all values in this equation, you can find out this T by theta, which is nothing but kt. So kt is known, I is known, right? Then you can find out for this system what should be Cc to make this system vibrationless, right? So Cc, you will get some numeric value here, and now if this numeric value you set here, means you take combination of mu al such that this becomes equals to numeric value of Cc, then this will make this system vibrationless, right? Is it clear?
Yes, sir.
Right, okay. So this is about finding critical damping constant. I am giving you another example as a assignment part. I'll also give you assignment 1 where we'll be showing you and just giving you data. This will be one assignment problem. You have one rod, you have pendulum. Now consider this rod is supported by one spring, and suppose now I want to make this system oscillationless, then I need to find out some critical damping constant, and I need to set the critical damping constant equals to external damping C. This is K and this is M, and length of this wire is suppose L, right? Let me tell you, this spring, suppose O is the hinge point about which this can oscillate, then distance of spring from this point O, that is small a, from O, distance of this damper is suppose B, and this distance of mass center from O is L. So this much informations are given. You are asked to find out CC. So you can note this as your assignment problem. Then after, today we will start one new, or we will define one new parameter which is called as logarithmic decrement, which is essential to find out damping ratio experimentally of any system. So note this problem and then let me know if you note this, then we go further.
8 minutes.
Yeah, take your time, no problem. So I'll be providing you assignment 1. In that assignment 1, this will be one problem. So I am informing you this problem well in advance so you can start solving this.